Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. Yang berbahagia Prof. Dr. Muhammad Roslan bin Sulaiman, Naib Chancellor Universiti Putra Malaysia. Yang berbahagia Prof. Dr. Hazandi Abdul Hamid, Dekan Fakulti Perhutanan dan Alam Sekitar. Yang berbahagia Prof. Dr. Ahmad Makmom Abdullah yang akan menyampaikan syarahan inaugural pada hari ini. Ahli-ahli pengurusan fakulti dan para penonton yang dihormati sekalian. Selamat datang dan menonton majlis syarahan inaugural oleh Yang berbahagia Prof. Dr. Ahmad Makmom Abdullah. Untuk makluman semua, majlis syarahan inaugural ini diadakan secara atas talian mengikut norma baharu dan dipancarkan secara langsung melalui Facebook UPM dan Facebook Fakulti Perhutanan Alam Sekitar. Tuan-puan dialu-alukan untuk menekan butang like dan share halaman-halaman Facebook tersebut. Seterusnya, bagi memohon keberkatan majlis pada hari ini, majlis mempersilakan Dr. Abdul Muhaimin bin Amiruddin untuk memimpin bacaan doa. Dipersilakan.
Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. Al-Fatihah. A'udzubillahi minasyaitonirrajim. Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Ar-Rahmanirrahim. Maliki yaumiddin. Iyyaka na'budu wa iyyaka nasta'in. Ihdinas siratal mustaqim. Siratal ladzina an'amta 'alaihim ghairil maghdubi 'alaihim waladdallin. Amin. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Hamdan yuafi ni'mahu wa yukaifu mazidah. Ya Rabbana lakal hamdu kama yanbaghi jalal wajhika wa azimi sultanik. Allahumma salli wa sallim ala Sayyidina Muhammad. Salatan tunjina biha min jami'il ahwal wal afat. Wa taqdi lana biha jami'il hajat. Wa tutahhirna biha min jami'is sayyiat. Wa tarfa'una biha indaka a'lad darajat. Wa tuballighuna biha aqsal ghayati min jami'il khairati fil hayati wa ba'dal mamat. Wa ala alihi wa sahbihi ajma'in. Ya Allah Al-Wajid, Ar-Rahman, Ar-Rahim, Asy-Syakur. Sesungguhnya kami memanjatkan kesyukuran di atas segala nikmat dan rahmat yang telah Engkau kurniakan kepada kami, kedua ibu bapa kami, ahli keluarga kami, sahabat handai kami, guru-guru kami, serta seluruh warga Universiti Putra Malaysia. Ya Allah Al-Mu'iz, Kau berikanlah kami kehusyukan di syarahan inaugural yang berbahagia Prof. Dr. Ahmad Makmom Haji Abdullah pada hari ini, supaya kami tergolong dalam kumpulan yang Engkau muliakan serta Kau muliakan juga semua yang terlibat dalam menjayakan syarahan ini, Ya Allah. Ya Allah Al-Fatah Al-Wadud, kami mohon kepadamu, Ya Allah, supaya syarahan inaugural Prof. Dr. Ahmad Makmom Haji Abdullah ini Kau berikan kelancaran, dimudahkan dan di akhirnya beroleh kejayaan. Ya Allah Al-Basid, Kau buka luaskanlah pintu-pintu ilmu supaya dapat kami manfaatkan dalam ibadah pekerjaan kami sebagai sebahagian usaha kami meningkatkan kecemerlangan diri serta Universiti Putra Malaysia dalam kuasa-Mu Al-Khaliq. Ya Allah Al-Muqid, Kau bukakanlah jalan kejayaan serta kekuatan kepada kami dan generasi selepas kami untuk kami memartabatkan serta mencintai ilmu-Mu, Ya Allah. Ya Allah Al-Qudus, Kau sucikanlah serta Kau pelihara hati kami sepanjang ibadah pekerjaan kami di Universiti Putra Malaysia dan hidup seharian kami bersama keluarga, sahabat handai dan guru kami supaya kami menjadi hamba yang Engkau redai. Allahumma inni a'udzika minal barasi wal jununi wal juzam wa min sayyi'il asqam. Rabbana zalamna anfusana wa illam taghfir lana wa tarhamna lanakunanna minal khasirin. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azabannar. Wa sallallahu ala sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. Walhamdulillahi rabbil alamin.
Majlis merakamkan ucapan terima kasih atas bacaan doa itu tadi. Para penonton yang dihormati sekalian, majlis dengan segala hormatnya mempersilakan Yang berbahagia Profesor Dr. Muhammad Roslan bin Sulaiman, Naib Chancellor Universiti Putra Malaysia, untuk mempengerusikan majlis syarahan inaugural ini dan seterusnya menjemput Yang berbahagia Profesor Dr. Ahmad Makmom Abdullah untuk menyampaikan syarahan beliau. Majlis dengan segala hormatnya mempersilakan.
Terima kasih saudari pengacara majlis. Assalamualaikum warahmatullahi wabarakatuh dan selamat pagi. Yang berbahagia Profesor Dr. Hazandi Abdul Hamid, Dekan Fakulti Perhutanan dan Alam Sekitar. Yang berbahagia Profesor Dr. Ahmad Makmom Abdullah yang akan menyampaikan syarahan inaugural beliau pada pagi ini. Pegawai-pegawai kanan Universiti Putra Malaysia, ahli pengurusan fakulti, tetamu-tetamu jemputan, rakan industri, para staf dan pelajar, sidang penonton yang dikasihi sekalian. Alhamdulillah, syukur kehadrat Allah kerana dengan limpah kurnianya, kita masih lagi diberi peluang untuk bersama-sama bagi meneruskan usaha dalam memertabatkan keserdanaan ilmu pada pagi yang mulia ini. Izinkan saya untuk membaca latar belakang Profesor Dr. Ahmad Makmom Abdullah dalam majlis yang gemilang ini. Profesor Dr. Ahmad Makmom Abdullah memperolehi ijazah sarjana muda dalam bidang ekologi dari Universiti Melaya pada tahun 1986 dan melanjutkan pengajian ke peringkat sarjana dalam bidang perancangan bandar dari Universiti Sains Malaysia dan bergraduat pada tahun 1991. Beliau melanjutkan pengajian ke peringkat Doktor Falsafah ketika bekerja sebagai pembantu penyelidik dan memperoleh ijazah kedoktoran pada tahun 1998. Beliau menyertai Jabatan Alam Sekitar sebagai pensyarah pada tahun 1998 dan pada tahun 2004 beliau dinaikkan pangkat sebagai Profesor Madya dan pada tahun 2018 beliau dilantik sebagai Profesor di Fakulti Pengajian Alam Sekitar. Pada ketika ini, beliau bertugas sebagai Profesor di Fakulti Perhutanan dan Alam Sekitar Universiti Putra Malaysia di mana beliau mengajar tentang pencemaran udara, pemencilan karbon dan perubahan iklim. Profesor Ahmad Makmom telah dilantik sebagai Timbalan Dekan Siswazah Pendidikan dan Antarabangsa pada tahun 2020 hingga 2021. Timbalan Dekan Akademik dan Hal Ehwal Pelajar pada tahun 2010 hingga 2020. Sebagai Ketua Jabatan Alam Sekitar, Fakulti Pengajian Alam Sekitar pada tahun 2009 hingga 2010 dan Ketua Makmal Akademik Hutan pada tahun 2005. Profesor Ahmad Makmom dilantik sebagai staf akademik UPM berdasarkan bakat dan minat mendalam dalam bidang pendidikan. Beliau mendapat latihan awal dalam pengajaran dan pembelajaran dan telah dilatih dalam perkembangan kurikulum dan teori pengajaran dan pembelajaran orang dewasa. Sejak itu, beliau terlibat secara aktif dalam program ijazah Bachelor Sains dan Alam Sekitar dari program 3 tahun kepada 4 tahun. Beliau juga terlibat secara aktif dalam perkembangan dan penyemakan program Bachelor Sains dan Teknologi Alam Sekitar. Profesor Ahmad Makmom telah melaksanakan pelbagai penyelidikan berkenaan dengan kesan pencemaran udara pada tanaman, ekofiziologi tumbuhan dan pemodelan pencemaran udara. Beliau telah mengendalikan dan menyelesaikan 8 projek penyelidikan yang dibiayai oleh Kementerian Pendidikan Tinggi dan Kementerian Sains, Teknologi dan Inovasi sebagai ketua projek dan 2 projek sebagai penyelidik bersama. Beliau memperolehi 5 grant universiti bagi membantu aktiviti penyelidikan pelajarnya. Beliau juga telah menjalankan penyelidikan kolaborasi bersama dengan Wageningen University of Research dan The Netherlands and Hamburg University of Technology berkenaan dengan peningkatan pembangunan kapasiti untuk pemindahan teknologi yang dibiayai oleh Suruhanjaya Eropah di bawah projek Asia EcoPro. Beliau juga merupakan penyelidik bersama dalam penyelidikan kolaborasi antarabangsa yang dibiayai oleh Kesatuan Eropah di mana di bawah program Asia Link bagi perkembangan modul pengajaran dan latihan untuk pengajian tinggi di sektor pengurusan sisa. Beliau juga merupakan ahli penyelidikan dan penyelaras pendidikan Universiti Putra Malaysia dalam kolaborasi pendidikan di bawah Memorandum Persefahaman bersama National Institute of Environmental Studies Jepun dan Institut Penyelidikan Perhutanan Malaysia. Di bawah MOU tersebut, beliau berkolaborasi dengan penyelidik dari Universiti Kyoto, Nara Women University, Yokohama University dan Forestry and Forest Product Research Institute Jepun mengenai biodiversity dan pertumbuhan semula hutan tropika yang dinamik selama lebih 10 tahun. Profesor Ahmad Makmom juga merupakan anggota kumpulan penyelidik tentang pencemaran udara dan rendah karbon bagi program masyarakat Jepun untuk promosi sains. Di bawah program ini, beliau diundang ke Jepun sebagai saintis pelawat ke Universiti Kyoto, Universiti Ritsumeikan dan Universiti Toyohashi sebanyak beberapa kali. Profesor Ahmad Makmom merupakan ahli jawatankuasa penasihat ilmiah untuk rangkaian pendepositan asid antara kerajaan di Asia Timur untuk bagi pemantauan tanah dan tumbuhan yang terjejas oleh pemendapan asid basah dan kering di Malaysia. Beliau juga merupakan perunding alam sekitar untuk Jabatan Alam Sekitar yang berdaftar dan terlibat dalam menyiapkan 16 laporan penilaian alam sekitar. Beliau juga diundang oleh Jabatan Alam Sekitar untuk mewakili Jabatan Alam Sekitar sebagai pakar subjek kualiti udara dalam menilai laporan penilaian impak alam sekitar secara terperinci. Beliau juga pernah menerima projek sokongan Kementerian Kewangan dari Jabatan Alam Sekitar untuk mewujudkan ambient air quality standard untuk hidrogen cyanida dari aktiviti pelombongan dan pemprosesan emas di Raut Pahang. Kepakaran beliau telah diakui di peringkat nasional di mana Kementerian Sains, Teknologi dan Inovasi telah melantiknya sebagai penilai untuk cadangan projek utama mempertahankan perancangan skema penyelidikan pasca doktoral. Kementerian Sumber Asli dan Alam Sekitar juga melantik beliau sebagai anggota jawatankuasa mekanisme pembangunan bersih sektor pertanian. Beliau juga merupakan ahli jawatankuasa teknikal mengenai kualiti udara TC8 dan perubahan iklim TC/Z/7 dan ketua kumpulan kerja aspek umum dan suasana sekitar untuk penyelidikan SIRIM. Pendidikan terkini beliau adalah berkenaan dengan pemodelan pencemaran udara yang menggunakan model MM5 Smoke CMAQ bersepadu untuk menilai kualiti udara yang menggabungkan sumber pelepasan, keadaan iklim dan perubahan guna tanah. Beliau telah mengarang lebih daripada 120 artikel, 38 proceeding, 29 laporan teknikal dan 27 bab buku. Beliau amat dikenali dengan pencapaian pendidikan apabila beliau telah menerima 7 pingat emas, 5 pingat perak dan 2 pingat gangsa di pameran penemuan, penyelidikan dan inovasi anjuran Universiti Putra Malaysia. Beliau telah menjalankan pendidikan tentang kerentanan, ketahanan dan penyesuaian masyarakat pasca banjir di semenanjung Malaysia selepas bencana banjir yang melanda negara kita. Beliau juga melakukan penelitian tentang pengaruh perubahan iklim terhadap petani padi di Malaysia dan mendapat manfaat bersama daripada hubungan antara perubahan iklim, pencemaran udara dan masyarakat. Dengan pengetahuannya, beliau telah menyantuni masyarakat melalui pidatonya tentang pencemaran udara, jerubu ataupun pencemaran rentas sempadan, kesedaran alam sekitar kepada komuniti kampus Universiti Putra Malaysia, para pensyarah Fakulti Sains Perubatan Universiti Sains Malaysia, sekolah dan agensi awam yang lain. Beliau telah berkongsi karya pendidikannya di peringkat tempatan dan antarabangsa di mana beliau mengambil bahagian sebagai pembicara utama, penceramah, ketua sesi pengulas, pelatih dan penyampai poster di dalam lebih daripada 250 persidangan, seminar, simposium dan juga bengkel. Dan yang terakhir, beliau telah dilantik sebagai pengurusi bersama persidangan antarabangsa tentang perubahan iklim pada tahun 2020 dan sebagai ahli jawatankuasa teknikal persidangan antarabangsa perubahan iklim. Sekarang, marilah kita mendengar syarahan inaugural oleh Profesor Dr. Ahmad Makmom Abdullah yang bertajuk Dust in the Air, Determination of Sources, Concentration and Distribution. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Bismillahirrahmanirrahim. Innal hamdalillah nahmaduhu wa nasta'inuhu wa nastaghfiruh wa na'udzu billahi min syururi anfusina wa min sayyiati a'malina. May yahdihillahu fala mudhillalah wa may yudlil fala hadiyalah. Wa asyhadu an la ilaha illallah wahdahu la syarikalah وأشهد أن محمدا عبده ورسوله اللهم صل على سيدنا محمد وعلى آل سيدنا محمد رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقهوا قولي. Assalamualaikum warahmatullahi wabarakatuh. Terima kasih kepada pengacara majlis Dr. Aisyah Abu Bakar dan terima kasih kepada Dr. Muhammin atas bacaan doa. Yang bahagia Profesor Dr. Muhammad Roslan bin Sulaiman, Naib Chancellor Universiti Putra Malaysia. Yang saya hormati Dekan Fakulti Perhutanan Profesor Dr. Hazandi Abdul Hamid. Yang saya hormati Dekan-Dekan, Timbalan-Timbalan Dekan, Div-Div terhormat, Tan Sri, Datuk Sri yang sudi menghadiri majlis pembentangan syarahan inaugural saya pada pagi ini. Yang saya hormati juga kepada Ketua Jabatan Profesor Madya Dr. Muhammad Firuz Ramli, yang saya hormati rakan-rakan seperjuangan, staf-staf sokongan, yang saya kasihi ahli keluarga yang dapat turut serta dalam majlis ini. Dan juga terima kasih kepada pelajar dan bekas pelajar di bawah penyelidikan saya yang sudi hadir ke majlis syarahan inaugural ini. Terima kasih. Yang berbahagia Naib Chancellor, izinkan saya untuk menyampaikan syarahan saya ini dalam bahasa Inggeris. Thank you. Ladies and gentlemen, it is my great pleasure and I feel honored to present my inaugural speech entitled Dust in the Air, Determination of Sources, Concentration and Distribution. The reason I select or choose these titles because of the importance of the dust as the standard pollution criteria pollutant in Malaysian air quality standard, especially PM particulate matter with the size of 10 micron and particulate matter with 2.5 micron in our air quality standard in TRIM 2 2018. Dust in the air or particulate matters in the atmosphere is not a new problem. It is old problem, but probably today we can understand some of the new solution, or we can figure out how we can solve this old problem with new solution. The third reason I choose these titles because we understand that the dust have serious effect on human health, especially during the haze phenomena. And the dust also have a synergistic effect with other pollutants, for example, sulfur dioxide, and it may enhance the effect of the other pollutants to human health. It is another new reason that I may suggest here is the particulate matter, suspended particulate matter 2.5 become the indicator of sustainable development goal for urban air quality. And with that, concentration of PM 2.5 used as the indicator of the urban air quality. I make my presentation more interesting by dividing the content into nationwide quality assessment, and after that I followed with air pollution emission and dispersion modeling, and followed by modeling PM10 distribution using remote sensing and GIS. And after that, I will share with you the modeling air pollutants dispersion from road traffic network using a steady state of air quality dispersion flow model. And finally, very brief, I will talk about the trajectory projection from transboundary haze from forest fire using a high split model. And after that, I will talk about the conclusion and way forward. Ladies and gentlemen, the nationwide air quality assessment is that we carry out the assessment using the historical monitored data. We have this continuous air quality monitoring station governed by the Department of Environment, and we request the data from the Department of Environment, and we analyze the historical monitored data. We use the API, Air Pollutant Index, as a reference of our assessment, and also recommended Malaysian air quality guideline. At that time, many years ago, before the air quality standard interim 2, 2018. I would like to highlight the results of our assessment. In 1997, especially in 1997, I chose this topic this year because this is the time that I started my interest in air pollution. Because in 1997, Malaysia experienced a very huge, serious disaster from haze, from transboundary pollution due to forest fire, especially in Sumatra and Kalimantan. So in 1997, almost all 29 continuous air quality monitoring stations recorded hourly measurement of particulate matter, PM10, exceeding the recommended air quality guideline of particulate matter 10 micron. At that time, 150 microgram per cubic meter. And the increase in the event exceeded the recommended air quality guideline, more than 50% to Kuala Lumpur and 12% in Klang and Gombak. And specifically, Sarawak, Kuching, experienced a serious API, Air Pollutant Index, more than 800, meaning that it is an emergency. Happened on 23rd of September 1997, where the state has declared the emergency with all the schools closed and all the outdoor activity also stopped. And the analysis of the continuous air quality data, we found that for the year 2001 to 2009, Shah Alam and Kuala Lumpur, at that time, on those periods, recorded the highest number of unhealthy days in Klang Valley. We applied the non-parametric statistic analysis of descriptive analysis, Spearman correlation, principal component analysis, and cluster analysis. This is a very good, suitable statistical approach towards the air quality data. We found that the analysis of year 2000-2009, the PM distribution in Klang Valley indicated that Klang and Shah Alam, we compared to Petaling Jaya and Kajang, Klang and Shah Alam shows higher mean concentration of particulate matters, PM10, as compared to Kajang and also Petaling Jaya. Cluster analysis on the temporal data series shows that PM10 concentration at Klang and Petaling Jaya and Shah Alam were clustered in group 1, meaning that they are having a polluted group. So the data series enough for us to conduct the PCA, principal component analysis, and we found that the PCA indicate that the PM10 pattern classified the continuous air quality monitoring station in Klang as having poor air quality. So the slide shows the cluster result of the cluster analysis. Later, we conducted nationwide air quality assessment in northern region of Peninsular Malaysia, involved the Perlis, Kedah, Pulau Pinang, and Perak. We analyzed all the air quality data from year 2002-2012, involved about 12 air quality monitoring stations under the governance of Department of Environment. We use the environmetric technique or non-parametric approaches such as principal component analysis, cluster analysis, and also factorial analysis. So from 2002 to 2012, we can observe the difference in the pattern of the particulate matter concentration in 2005 and 2006. Indicate a very significant difference due to transboundary pollution. From our cluster analysis, there are three classes of the station. Class 1 is the Sekolah Kebangsaan Cenderawasih, located in Prime Free Trade Zone. And this school is only located in the industrial area, classified as non-conducive environment, or classified as not good air condition, and it is a class 1. Class 2 involve the air quality monitoring station in USM, Langkawi, Alostar, Perlis, and Taiping. And class 3 involve 4 stations, Tanjung Malim, Manjung, Tasik, and Pegoh. And this class 3 classified as moderate air quality condition. So the contribution of the air pollution in this station, class 3, is basically from the congested traffic, high population residential areas, and mixed industrial area. Using the non-parametric tools, we will be able to identify the influence of monsoon on the PM10 distribution. And we can observe the different wind pattern of monsoon. For example, we have the southwest monsoon in June and September, where they blew the pollutants from neighboring countries, and it contributes to the haze phenomena. And this pollutant increase the particulate matters, especially during those periods, June to September. And during northeast monsoon, during in November to March, which began the wet season, the numbers of forest fire also reduced, and the concentration of the particulate matter also reduced. So that is the influence of the monsoon. And we found that the factor 1, sulfur dioxide, nitrogen dioxide, and ozone, and followed by the PM10, were the major contributor to which contribute 76%, and factor 2 gives 23% of discrimination. So we found that the concentration of PM10 in northern area is not the PM10. The major air pollutant is from sulfur dioxide, NO2, and ozone, and followed by PM10. And this is because the emission from industries and from the road traffic is mainly sulfur dioxide and NO2 and ozone. So the difference in Klang Valley and also northern area is the PM10 as the main pollutants contribute to the degradation of the air quality. Ladies and gentlemen, I come to the next topic. This is air pollution emission and dispersion modeling. Air pollution modeling is a very important approach where we can estimate the relationship between the source and the effect, the distribution of the pollutant and the effect on the air quality. The air quality managers usually use the model to identify the source's contribution to air quality and also assist them in design effective strategy to reduce harmful air pollutants. So we said our research domain consists of 4 domains. One is the emission inventory and also the meteorological domain, and followed by the engine. This is the model, the air pollution transportation model, and finally the fourth domain is the impact assessment, as shown on the slide. This research framework we follow closely to arrange our work, especially in the emission inventory. For example, emission inventory, we use sparse metric operation kernel emission, which is in short smoke model to construct emission profile. And we use MM5 or Pennsylvania 5th generation mesoscale model to generate the meteorological profiles of the study area. And CMAC is the engine of this modeling, air pollution modeling. So the arrangement, we call it regional air quality management modeling system, or integration of smoke, MM5, and CMAC integration. This modeling system in Malaysia, especially in Malaysia and developing country, it is used to assess the air quality because we don't have enough resources. Compared to developed country, they use this regional air quality modeling for problem solving with corrective measures implemented in the integrated pollution and control program. So the important in this exercise is in the research is the air pollution emission inventory. So our regional air quality modeling system capable of assessing the relating complex atmospheric pollutant interaction and be able to produce simulation result for the related air pollutants, such as in this case, particulate matter. So our particulate emission inventory, we consider 2 main sources. One is the industrial area, another one is road traffic network. And we use a different road type, road class, different vehicle types, and different emission factors suitable for the energy used by the vehicle. So the domain of this study is identified using the CMAC, where we have to establish the grid system with subgrid 3 kilometer by 3 kilometer. So the sources of the pollutant in this grid, we classified into 2. One is the industries, another one is road traffic network. So the industries, we use top-down approach to establish the pollutant emission inventory. So the top-down, we use the national emission data from the Department of Environment report. So translate into the area or industrial area, and we calculate the emission per square meter per second. And another one is bottom-up approach is we use the road network, where we classified into traffic types of vehicles and intensity. Road network classification, federal, or is it federal highway, or it is state or highway, and also the length of the road inside the subgrid. So the operation, it is the vehicle kilometer travel and emission factors used to calculate the emission, together with the classification of the vehicle. So smoke model used to generate the emission profile. This emission profile is ready to use by the CMAC. Then the three models have to follow the grid system established under CMAC. So this is the class of the vehicle we use. We have identified 6 classes, vehicle classes, and we have this emission coefficient, gram of particulate matter PM10 per kilometer. So in Malaysia, this is the registered vehicle class by JKR and Road Traffic Network. So we produce a thematic map from this model, and you can see that the concentration, the red color is high concentration located in the Klang Valley at that time. And the whole Selangor, this is the map of the whole Selangor. When we produce the dispersion of the particulate matter PM10 distribution from road traffic network, you can see that the high concentration mainly focused in the Klang Valley. So another aspect of this modeling, integrated models, is the profile of meteorological of the study area. In our case, we use the whole Selangor. So the meteorological profile generated by MM5 by the preprocessors such as terrain, grid, and interface to generate the meteorological profile. For example, here, temperature profile. So we can see that it displays in terms of the spatial distribution, and we can see that the 70% of the area is higher, having high temperature at 2 o'clock, above 32 degrees Celsius. And about 32% of the Klang Valley having the temperature, experience the temperature below 27 degrees Celsius during the monsoon and intermonsoon. We calibrate the output of the model with the data monitored by Department of Environment, and it had a very strong correlation coefficient of value 0.72, indicating that this is a high pattern of similarity. So the model prediction, the actual monitoring results show the very similar pattern. The MM5 also produced the wind speed and wind vector prediction profile. This meteorological chemistry interface processor, MCIP program, managed to generate not only the distribution of the wind, but also the wind vector profile. We generate the intermonsoon, April in 2012. Example here, June in 2012 is the southwest monsoon, and October 2012 is intermonsoon, second intermonsoon, and this is the wind vector during December 2012, or we can say during monsoon of northeast. So with the meteorological condition and the emission, we integrate into the CMAX modeling, and the model we generate the spatial distribution of PM10 in our case. And spatial PM10 distribution, we also get the data from Department of Environment, from various stations in Klang Valley, and we interpolate data from continuous monitoring monitoring station. We interpolate data into spatial distribution, and we compare the PM10 from continuous air quality monitoring station with interpolation of the ground measurement data, interpolate into spatial distribution. And we found that the spatial distribution between the integrated model and also from the interpolation of monitored data, we can see the huge gap between the two map or isoplat. And the difference we can address it is because of the insufficient of the emission inventory. Yeah, we use only two type of emission that we can confident and we can address the data, which is the industries and also emission from road traffic network. So we cannot recognize the another half of the emission is from the fugitive element. This fugitive element might be confounding factors that indirectly affect the PM10 distribution. And this fugitive may contribute also to the high uncertainties between the CMAC outputs. And we compare between the two, we can confirm that the PM10 emission we do not include in this modeling system is the emission from boilers, from incinerators, from quarries, from cement industry, from construction activities, off-road vehicle movement, machineries operation, wind erosion, and the burning of agricultural waste. So with all those emissions not included into the regional air quality modeling, we will not be able to match the simulated data with the interpolation of monitored data. So this is the future activities that is recommended to the new scientists, that they can look into this emission and establish the emission from fugitive, from unknown sources. Ladies and gentlemen, I would like to talk about the modeling of the PM10 and PM10 2.5 distribution using remote sensing and GIS. After my explanation about the assessment of the continuous air quality monitoring data, that is the best approach to assess the air quality because we have the ground measurement, direct measurement towards the air quality. Second, we use model to relate the source of pollutants and also the effect of the pollutants. And another one is this is also becoming a very interesting approach where we can utilize the satellite images, remote sensing and the GIS. Because the satellite approaches seem to be the best way for monitoring the patterns and transport of aerosol, largely due to extensive spatial coverage and reliable repetitive measurement. So we review the abilities of the satellite instrument that have been designed for remote sensing of aerosol, their prospect and their limitation of the limitation of the sensors, their data results, and their application in air quality monitoring. So we review this, the Earth Observatory System, EOS, and we have the EOS Terra from NASA, where they generate the moderate resolution image spectrograph, or in short, EOS MODIS. Another one is the multi-angle image spectroradiometer, MISR, and also Landsat thematic mapper, TM, for band 1 with 30 meter resolution. We also review the ADIOS folder or polarization and directionality of the Earth's reflectant. Yeah? It is from Midori. We review all the prospect of using these remote sensing images in our PM10 distribution prediction. So the first exercise, we use the Landsat Enhanced Thematic Mapper Plus, ETM Plus. So the purpose is to establish a model to estimate the particulate matter PM10 from this thermal infrared band, from the Landsat Enhanced Thematic Mapper Plus, ETM+. Our assumption is that the calibration of the thermal infrared band of Landsat ETM+ depends on the amount of suspended particulate in the air. It is assumed that the thermal value recorded at any pixel does not represent the true ground radiant temperature, due to the fact that the temperature is influenced by the atmospheric pollution. They are scattered or absorbed by suspended particulate, especially by suspended particulate. So we use this principle, the ground surface temperature band 6 retrieval from the images could be affected by the PM10 concentration, and ground surface temperature and wind speed may affect the PM10 concentration. We use nonlinear correlation coefficient, NLCC, to gain better understanding of the relationship between the wind speed and ground surface temperature, PM10 concentration, and ground surface temperature band 6 retrieval from the images. So the data, we have this ground data of particulate matter, PM10 concentration from Department of our Environment, and we conduct this assessment to 3 locations, 2 in Iran, another one in Malaysia. One is in Tehran, another one is in Sanah. In Malaysia, we have the ground station, we have the ground data, PM10 concentration from Department of Environment. In Tehran, we have this data from Iran Department of Environment, and also from the Iran Meteorological Organization. They provide the ground surface temperature, and the retrieval is from the Landsat ETM. The ground station temperature, the ST band 6, and also the temperature of the nearest dark pixel group, band 6, also from the Landsat ATM+. Ladies and gentlemen, the image have to be rectified with the GIS. The remote sensing have to be rectified. It is the normal procedure. So band 6, band 5, band 4, and band 3 of all images were rectified to UTM coordinate, Universal Transverse Mercator. For Iran, it is we use datum WGS 84. Iran is located at the zone 38 degree north and 39 degree north for Tehran and Sanah. While Kuala Lumpur or Peninsular Malaysia is datum WGS 84, zone 47 degree north. So this later we geo-reference using the nearest neighbors resampling algorithm. In Iran, we based on the topography map, 1 to ratio to 25,000 meter, and for Malaysia, we use 50 ground control point. So band 4 of all images were utilized for qualification of the monitoring ground station by linking the band. Band 5, 4, and 3 were used to show the true colors as shown in the slide. How we can mimic the true colors of the study area. So we developed the model by establishing this argument. The first one is that ground surface temperature band 6 from the retrieval, the Landsat retrieval, is a function of the ground station temperature, the atmospheric effect of the emission of the ground station, AEEG, S, and the emissivity of the station, ES, and they represent as the following equation. And the temperature near dark pixel group, band 6, is a function of the dark pixel temperature itself, atmospheric effect on the emission of the dark pixel, AEDP, and the emissivity of the dark pixel. In this case, we followed the Scott et al. In 2001. We use as 0.985, the emissivity of the dark pixel. So the equation shows in the slide. And finally, the predicted particulate matter is equal to ground surface temperature band 6 plus with temperature near dark pixel group band 6 and also the ground surface temperature. So minus the ground surface temperature. So we understand that ES, emissivity of the station and dark pixel temperature also part of the result. And finally, we have the first model predicted particulate matters equal to the atmospheric effect on the ground station plus with the atmospheric effect on the dark pixel plus the emissivity of the dark pixel, in this case 0.985, plus the emissivity of the station and dark pixel temperature itself. The second model assumed that any difference between the ground surface temperature band 6 and ground surface temperature itself may be due to the atmospheric effect on the emission of the ground station, and also show the atmospheric effect of emission of the ground station and emissivity of station, and we have the prediction of particulate matter equal to the atmospheric effect on the ground station plus the emissivity of the station. And the third one we establish, we eliminate the emissivity of the station, which depends on the temperature, emission angle, and wavelength. So we have the third equation as particulate matter, predicted particulate matter. It depends on the dark pixel temperature, atmospheric effect on the dark pixel, and also the emissivity of the dark pixel minus the atmospheric effect on the ground station and emissivity of the station. So with this model, we analyze the data for Tehran, Sanah Dasht, and also Kuala Lumpur. And we found that the standard deviation in ground surface temperature and ground surface temperature band 6 for Tehran much higher than standard deviation for Sanah Dasht and the Klang Valley. We can understand that the seasonal differences could be the cause of high standard deviation, because the minimum standard deviation obtained in winter and maximum standard deviation was in summer. And also the high standard deviation because of the low thickness of vegetation cover in winter and high thickness in summer, affecting the ground surface temperature and ground surface temperature band 6 image from Landsat. So Klang Valley is a very good one. Show this low standard deviation in ground surface temperature and ground surface temperature band 6 due to its temperature condition always being 20 to 21 to 36 degrees throughout the year. So in summary, we can say that the thermal band of Landsat ETM Plus is very useful and reliable in determining the PM10 concentration and investigating its distribution. Using this method and the GIS environment, researcher will be able to overcome the Landsat ETM Plus problem in thermal band with regard to some spots having no digital numbers values. Ladies and gentlemen, we continue our assessment using this remote sensing because the development in the satellite images, because we have these MODIS, they measure the AOT, aerosol optical thickness. And these images from the MODIS, Terra, we can use to establish the AOT at the band of 0.55 micrometer wavelength. So we use that to relate with the content of particulate matters in the atmosphere. So we compare with the ground measurement and real-time PM concentration by the continuous air quality monitoring station under the OE, and we use the AOT from MODIS. So during this early exercise, we used nonlinear correlation, and we found that the nonlinear correlation was not very strong correlation, but there is a positive correlation between the AOT and also the PM10 concentration in the study area. So we used the Victoria Kuala Lumpur station, where we have the correlation coefficient for Victoria is about 0.594, and compared to Cheras, and we have the correlation of R square equal to 0.332, and Gombak station is R square 0.359. So we transform into the spatial between the weekdays and weekend, and then we can see the surface map of distribution of the pollutants. So it shows that the MODIS AOT and the PM10 can be used or can be related to study or to assess the PM10 distribution. So later, because of the development in the satellite images, we explore further. We use the MODIS derived AOT also, but this time the AOT data from aerosol robotic network. It is the ground measurement of aerosol or optical thickness. So they have this data, and we can analyze the AOT from MODIS and calibrate with the AOT data from aerosol robotic network, for example, from Aeronet. There are two stations in Malaysia. One is in University Science Malaysia, USM Penang. Another one is the Aeronet in Kuching, Sarawak. So the average PM, in this case, we use PM10 and PM2.5. We get the data from Department of Environment, and we relate the AOT with the PM10 distribution. And the AOT from the MODIS calibrated with the AOT from Aeronet robotic network. So the data from the satellite you can download from this NASA-operated Giovanni portal, addressed on this slide. And this is the window where you can select the images from the website. It's very important that if you want to study the whole Peninsula Malaysia, we have to look at the study area covering the whole Peninsula Malaysia. So we calibrate the AOT. We use the station, continuous monitoring station by the Department of Environment. They measured the PM2.5. In 2013, they have this data, and we use this AOT measurement from Aeronet. Unfortunately, the MODIS AOT retrieval in a band of 550 nanometer. But if you look at the Aeronet data, they don't have the band of 550. So between 500 to 675. So we had to translate the data to AOT to the band of 550. So the equation established that AOT is a function of PM2.5. In this case, I show you the relationship between the PM2.5 and the AOT, aerosol optical thickness. We assume that the PM2.5 concentration is thoroughly combined in the atmosphere, and the cloud cover is not there or absent from the sky. So it is the AOT and PM, as a function of the height of the boundary layer, the ratio of ambient, and the radius of the particles. And with that, we finally use the multilinear regression, and we generate the relationship between PM2.5 hourly and daily with the relationship with the MODIS AOT and the wind speed wind direction, and also the temperature and relative humidity. So using the multilinear regression, we managed to establish this equation, and spatially you can transform the PM10 distribution or PM2.5 distribution using the image from the MODIS. So in summary, it is concluded that MODIS has potential capability in monitoring ambient PM10, and it is very good because we can use this technique to location where we don't have the ground measurement station. And satellite data is able to recognize the regional distribution of suspended particulate matter over a large area. In this case, for example, you can use the whole peninsular Malaysia. And the MODIS AOT somehow tend to overestimate the ground level AOT value. So finally, we can say that the satellite data is an excellent tool for study the particulate matter distribution and air quality over a large area. Ladies and gentlemen, I would like to share with you the research activity that we conducted in the Klang Valley, which is modeling the particulate matters, PM10, and also heavy metal content from the road traffic network in Klang Valley using emission inventory and also a steady state flow model. In this case, the steady state flow model is A-mode model, and this A-mode model is a Gaussian model. And when we call it a Gaussian model, because the model assumes that the stable boundary layer, under the stable boundary layer, the concentration distribution to be Gaussian in both verticals and horizontal, meaning that the plume, when they release, they are expanding to horizontally and vertically, and the shape that they generate is the shape of the Gaussian. And the second assumption is that the convective boundary layer, CBL, the horizontal distribution is also assumed to be Gaussian. And the third assumption that the vertical distribution is described by Gaussian probability density function. In this model, the plume, the steady state flow model, or in this case A mode, it is the atmospheric stability determined in this system by albedo, Bowen ratio, and length of surface roughness. Albedo is the fraction of the total incident solar radiation reflected by the Earth's surface. Bowen ratio is the ratio between the sensible heat due to conduction and convective and latent heat. This is based on the Earth's surface. And the length of the surface roughness is the height at which the mean horizontal wind speed is 0. So this model have two main pre-processing. One is the AMAT, they call it AMAT preprocessor. Another one is AMAT. The AMAT is to generate the meteorological data. AMAP is another one is to generate the terrain and take into account the receptor distribution. So important is that the land use type of the study area characterize the albedo, Bowen ratio, surface roughness, and value. And this is the atmospheric stability determined by these factors. And indirectly, it is determined by the land use type of the study area. So in the pre-processing process, number one is the AMAT. The hourly surface and upper air data, including the total cloud cover, opaque cloud cover, and dry bulb temperature, dew point temperature, atmospheric pressure, as the input into this AMAT preprocessor. And this preprocessor will produce, one is the surface file, another one is the profile profile file. The surface file, it will generate the sensible heat flux, surface friction, convective, surface roughness, length, bone ratio, albedo, and so on. And the profile file will consist of height, wind direction, wind speed, temperature, and standard deviation. So I show you the model window. There are 3 windows here. One is the background windows, is the air map, show the map and also the distribution of the receptor. And the middle and the front window is the information about the emission of the pollutant from that particular area. So the second pre-processing in air mode is the air map. This air map preprocessor take into the models, the processing system, the input data. The input data is the digital elevation map. So you need to have the digital elevation map where you have the X, Y, Z, the coordinate, lat long, and also the concentration or the emission of the pollutant. And also, second component is design of the receptor, where the receptor located. And this model considered Eulerian types of model, where you use the grid, and the grid can be distributed in a polar style or Cartesian, or homogeneous Cartesian or heterogeneous Cartesian, or you can use discrete receptors. And information such as the surface roughness, building, hill, trees, and obstruction, we know that it will enhance the distribution of the pollutant or reduce the distribution of pollutant. So this AMAT will process the data, and they will determine the planetary boundary layers. So when we have the land surface, because the land surface will determine the movement of the air in the planetary boundary layer through the momentum, vertical exchange, because it will affect the exchange of the momentum, heat, moisture, and mass. And the degree of the convective turbulence usually determined by the amount of surface heating in the planetary boundary layer. And we understand that most of the anthropogenic activity occurred in the planetary boundary layer. So that's why the reason we can see that the mixing height usually elevated in the day because of the greater turbulence and considerable mixing of the air compared to the night time. One of the components in the models that we need to key in is the emission from the road network. So we take into account the non-exhaust particulate matter emission. We estimate from the emission factors and the vehicle activity. Second, the emission from the resuspension dust on the paved road surface. And also the third one is the particulate emission factor from brake and tire wear. So the similar exercise is that the sample from this category, we analyze the heavy metal content of the PM10. So the formula we use for the non-exhaust particulate matters from vehicular activity, we take into account the VKT, vehicle kilometer travel, and also the emission factors. This is the density of the traffic. For example, in Selangor, we use the density for each district because the JKR is monitor the they conducted the traffic survey for each district in Selangor, and then we can determine the traffic volume and the activity of the traffic. For the PM10 emission factor from the resuspension of dust and paved road, we look at into the surface silt content. We need to have the multiplier. For example, in this case, multiplier. We have this multiplier from AP42, well known about the emission, and also the numbers days of where we have rain or not. And the third one, the particulate emission factor from brake and tire wear. And the emission is based on the numbers of vehicle, the type of the emission from particular vehicles and particular grid. Yeah? And then this is a Eulerian, and also use the grid system. We had to calculate the emission for each grid. So the similar exercise for estimation of heavy metal from exhaust emission. We have this heavy metal emission from fossil fuels used, and how much the fuel consumed by each type of vehicle. I mentioned again the 6 classes of vehicle in Malaysia. So what type of fuel they use, and then we use the emission factor for heavy metal emitted from the every kilogram of the fuel used. And the fuel consumption estimate from the following equation, where we have the average annual vehicle kilometer travel. So how much the petrol or diesel they use. And we calculate every single grid in Klang Valley. So the results, we can see that the dispersion of the particulate matters in this study area. So the isoplat, we call it isoplat, we can overlay with the actual map from topography map or Google map. You can overlay this dispersion distribution of the particulate matter, PM10. And you can see that the center of this is Klang Valley, where we have truss, we have UPM, Unit 10 also. So the concentration mostly located in front of the Unit 10. This is the area where we have the high traffic volume. And also we have this high concentration of PM10 distribution in Kajang, Cheras, and distribution of the pollutants towards the Shah Alam. And we can see the non-exhaust source particulate matter distribution, and also from resuspended dust and brake, based on the equation that we use. And also this one is the similar pattern shows by the heavy metal. We analyze the arsenic, plumbum, cuprum, nickels, and cadmium, and cobalt. So the similar pattern shows by this heavy metal distribution, because it's based on the particulate matter PM10. Okay. So we can generalize the distribution of the heavy metal. For example, here maximum concentration of manganese, yeah, observed at the western and southwestern side of the domain, study area, heading towards the Shah Alam and Subang, and the central and southwest eastern side of the domain near Tras and UPM highway. Yeah, so that is how the pollutant disperse. And also this one is heavy metal distribution. So finally, we can say that, yeah, the based on this isoplat, you can generate isoplat from the Ahmad model can generate the hourly distribution, or you can generate monthly distribution, or seasonal or annual distribution. So based on the standard or requirement that you are supposed to generate. So this model allowed us to generate this kind of isoplat. And interpretation of this isoplat is to calibrate with the actual measurement, ground measurement. So in summary, we can say that the spatial distribution of PM10 concentration and heavy metal has been influenced by the topography, including the land use and the nature. The nature is the physical factors, the prevailing winds in terms of its direction and speed. And in our study, northwestern wind direction diminish while they travel through the Titi Wangsa range. During this season, they move to Klang Valley. They pass through the Titi Wangsa range and they come into the Klang Valley. And they divert the direction toward the southeastern direction. And what happened is that they carry the pollutant in the Kuala Lumpur, moving toward the southwestern part. So the city that we affected is the Shah Alam and Klang. And during this season, the pollutant carried from the KL center to Shah Alam and Klang. And during the southwestern, they move southwestern monsoon, wind carried the different way, the other way, from the Klang to Shah Alam, move towards the Ceras and Kajang. So that is the result or the output from Ahmad modeling. So finally, I would like to share with you this high split model. This is the technique to determine the transboundary haze. We can predict the movement of the pollutant from the forest fire or hotspot. Because this model, they call it high split, it is hybrid single particle Lagrangian integrated trajectory. They use the center of the plume move towards the downwind direction, and this trajectory we can calculate the concentration, and we can predict where it goes based on the atmospheric condition. So we need to have the meteorological data, and this model is developed by NOAA and Australian Bureau of Meteorology, and the model be able to predict the movement of the particles about 96 hours interval. And it is very suitable for the prediction of haze from the forest fire, can be in Sumatra or the forest fire from the Kalimantan. And the hotspot data is based on the NOAA 18 satellite images. It is processed by the ASEAN Specialist Meteorological Center. It is the center agreed by the ASEAN country. And this center produce the hotspot immediately, and you can forecast the dispersion of the haze from the hotspot. And the forecast meteorological data, we can get it from the resource laboratory link of the NOAA as one of the input for the hybrid or high split model. So this is the pictures where satellite images where you can see the red spot, and the haze in the atmosphere, how the haze move in the atmosphere in Southeast region, where we have on our left, top left, is the Peninsular Malaysia, and we have the hotspot in Kalimantan and also the Sumatra. And this is the model how the concentration calculated. We take into account the deposition, take into account the because this one is trajectory. Every 1 hour you will calculate the next concentration and the next levels of the particle towards the wind direction. And I would like to share with you the simulation of this slide. You can see that the movement of waves we predict from hotspot in Kalimantan on 90th October 2015. So we can see that within 48 hours, the pollutant from this hotspot in Kalimantan can arrive towards the Kuala Lumpur. And how they travel, you can see the concentration of the particulate matters, PM10. And also this one is on the 20th October. We also simulate the how the dispersion of the haze. Yeah, so you can see that the movement of the particulate matters, the major contributors of the forest fire. Yeah, so or we can generate as like this with the on 90th October 2015, for example, we have the total hotspot 413, and we simulate from those hotspot, and then you can see that how the pollutant travel to within 96 hours. And this is also in on the 22nd of October, and after that on the 26th October. Interesting, if you look at the pattern of the pollutant movement on the 26th October, the particles move from the Kalimantan, will hit Singapore and part of the southern part of Peninsula, but they're not coming back to the Peninsula, but they go straight to the Hindi Ocean. So usually most of the part in Peninsular Malaysia, they have the good air quality as compared on the 22nd of October, where we have high concentration of the particle, because you can see that the movement of the particle moving towards the Peninsular Malaysia. So finally, can we determine the concentration, the distribution of airborne particulate? Come back to the dust, the titles of today. I would say that using the high-speed model, just now you can see that we can determine the concentration, dispersion of the pollutants, and where they come from. And I mentioned again the WF CAM modeling system. I use the smoke, MM5, and CMAC, whereas nowadays there is advanced modeling system. We call it WRF, is weather forecasting, coupled with chemistry model, and this model directly can determine the dispersion of the pollutants from the source. And remote sensing is a very good tool, especially MODIS, Landsat ATM Plus, and another one, hyperspectral. And model, other types of models, not only the air mode. Now there is development of the new models. It is from the traffic network. And I noticed that this is new, not yet available to to the community, research community. It is very recent. They established the model from the road traffic network. Of course, the statistical analysis is the best way of utilize the existing data. The continuous air quality monitoring station, they generate the historical data. My advice is that the statistical analysis to be used on this data series, and it will determine the concentration distribution of the particulate matter. So in summary, I think I go straight to the conclusion and the way forward. My recommendation after my presentation is that we have this ambient air quality standard in TRIM 2, 2018. It is this new air quality standard require high resolution information on air pollution level to provide not only detail but also the pollution level. At this moment, we have a very limited station at one city, one station. It is called macro level, but we need the pollution level for individual street, micro level. So that when we establish the ambient air quality standard for each, especially in the city area, we have the high resolution information. Not only the horizontal, but also the monitoring, continuous monitoring station vertical. And definitely it will cost us the expensive, because this one we had to establish the many station and individual street. So it is good to use a model, for example, the computational fluid dynamic used in the city area, where you can visualize over the street and surface and building facade, so that the pollution variation in the between the building and the road in the city area, we can establish using the computer fluid dynamic model. And the monitoring is to validate the model. This is my point, that into the future, that we need to use model, but the station is to validate the output of the model. And advanced model, for example, WRF-Chem, weather research and forecasting model, coupled with the chemistry, it is good to use. And it is using the new technology in the computer system, and it's very easy compared to the previous modeling system. For example, my regional air quality modeling system, I use the SMOKE, MM5, and CMAC. It is written in Fortran, and then you have to use operating system, Linux operating system. And it is not a common operating system, and not many people be able to utilize this kind of model. And also not to miss the planning effective measures to improve urban air quality. Such information will help decision makers to optimize the urban environmental design. So we don't have that integration between the urban design and the environment, especially the local authority and the Department of Environment. That is my conclusion, and also my suggestion for moving forward in this kind of thing. Finally, I would like to acknowledge my staff and the student of Faculty of Environmental Studies, not only the Faculty of Forestry and Environment, but I would like to say thank you to the staff of the Faculty of Environmental Science, Faculty of Science and Environmental Studies, Faculty of Environmental Studies and Faculty of Forestry and Environment. I have three faculty. The first one, Faculty of Science and Environmental Studies, Faculty of Environmental Studies, and Faculty of Forestry and Environment. Thank you to all the staff, and thank you to the lecturers and also the dean. And I would like to say thank you to Frame Forest Research Institute of Malaysia for giving the opportunity to use their facilities, and also MOSTI, Ministry of Science and Technology, provide me the research grant, and also INET, Asia Network in Acid Deposition, where they allowed me to be the members of the contact person of the country to represent the country in this network. And Shirim, thank you very much for giving me the opportunity to be the leaders of the working group of general aspect and ambient atmosphere, and also the members of the technical committee of air quality and climate change. I would like to say thank you to Department of Environment especially for giving me the opportunity to become their representative for especially the environmental impact assessment. I would like to express my thanks to my late father, Haji Abdullah bin Haji Dahlan, inspired me into continue my study towards the PhD, and also my late mother, Rukiah binti Haji Jaafar, who always pray for me, for my safety, always teach me how to be humble, be patient, and my wonderful wife, Madam Rasia binti Mahbub, and my children, Amir Rashid, Nur Atika, and Daniel Akmal, for always supporting me, always with me whatever situation, and support me in my pursuit for the career. And I also like to say thank you to Professor Emeritus Dr. Muhammad Awang, my mentor, and the late Professor Akil Purukawa, also my mentor, and Mr. Samsudin Johan, worked with me for many years in my research activity. And I not forget to say thank you to Deans, Professor Mak Nasir, Professor Mak Zarin, and Associate Professor Dr. Ramzani Abdullah. And I would like to address my appreciation to my co-researcher involved with me in many kind of research, Professor Dr. Mazuki, Professor Maria, Associate Professor Dr. Muhammad Firuz, Professor Wanwa Azmin, Professor Azizi, and also good friend of me, Associate Professor Dr. Tengku Haniza, Tengku Ismail. And also my thanks to collaborators, mentors, and friends, Professor Mak Soka from Kyoto University, Professor Stegman from Technical Technical University of Hamburg, and Professor Dr. Toshinori Okuda and Takeshi Yamada, Professor Takeshi Yamada from Hiroshima University, and Dr. Naishen Liang. We have a very good research collaboration for almost 12 years, more than a decade in research collaboration. And with that, I said thank you for giving me this opportunity to present my inaugural speech. The mistake is mine, and the good is from Allah Subhanahu Wa Taala. Wabillahi taufiq. Wassalamualaikum warahmatullahi wabarakatuh. Thank you very much.
Majlis merakamkan jutaan terima kasih kepada Yang Berbahagia Profesor Dr. Muhammad Roslan bin Sulaiman di atas kesudian mempengerusikan syarahan inaugural Yang Berbahagia Profesor Dr. Ahmad Makmom sebentar tadi. Para penonton, dengan itu berakhirlah sudah syarahan inaugural pada hari ini. Sekali lagi, majlis merakamkan ucapan terima kasih di atas kesudian anda semua yang mengikuti secara atas talian. Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. #kita jaga kita.